Okay, so better understand stereochemistry, okay, we're gonna have to understand optical activity, what that actually means. We said that chiral molecules, they are enantiomers, right? These compounds have identical physical and chemical property, and the only difference between these compounds is that they rotate the plane polarized light in opposite direction. So let's look at that. So these two compounds are called enantiomers, and if you look at it, you can draw a mirror image right in between, as a or mirror in between. So they look like a mirror image of each other, and they are in fact mirror images of each other, right? Pretty much anything can have a mirror image, right? Anything, you can put anything in front of a mirror and it will have an image, unless and until you are of course ghost, right? But anything else will have, any subject, any object will have a mirror image. Molecules will also have a mirror image. There is no but the question is, are these mirror images superimposable? Now in this case they are not, because this is a chiral molecule, right? This is a chiral center. It has 4 different groups attached to it. So you have an OH group, H, and then you have ethyl and CH3. 4 different groups attached to it, or different groups are atoms. That means this is a chiral molecule. If you draw the mirror image of it, you're gonna get this molecule, and these two are called as enantiomers or enantiomeric pair. Okay, this is a very simple molecule. In fact, this is a 2-butanol, 1 2 3 4 carbons, and OH group on the second carbon, right? It's a 2-butanol. This is called as S and this is called as R. Again, we're gonna see why that is these terms are given to you, but for now just say that for differentiation, to differentiate the molecules, we're gonna say that this is an S enantiomer and this is an R enantiomer. Okay, so now if you look at their physical properties, they have identical, both of them have identical physical properties. Their boiling point identical, yeah, density also identical. When I say identical, that means exactly same up to the decimal, few decimal down. If you can accurately measure the melting point up to 5 decimal, then you can see that both of them will have exactly same boiling point up to the 5 decimal or 10 decimal, or depends upon how accurately you can measure it. Yeah, so they have exactly same physical property. We said that they also have exactly same identical chemical properties, right? Now what sets this enantiomers apart? It looks like they are the same molecule, because only same molecules can have identical physical and chemical property, isn't it? But they are different, right? Because you can't superimpose them. As a result of that, we need to prove that they are different. So what set these enantiomers apart? Okay, the answer is that they interact with plane polarized light in a different way. Yeah, and so essentially what is plane polarized light? So we have ordinary light bulb, let's say, and we can visualize its emission, right? This is obviously going to give out waves of light, yeah, and we can visualize its emission as light that is vibrating in all possible ways, infinite number of planes, right? Infinite number of planes. So this is vibrating, these planes are vibrating in infinite number of planes. Now as it turns out that there is an instrument called as polarizer. In this particular case it is just shown as a slit, right? But there is an instrument which can actually polarize the light. That means you can rectify these planes into a single plane, right? And it comes out as a slit actually, but it's a lot of mechanism goes on. I don't know exactly the how it works. It's a ancient instrument actually, we don't use that anymore, but there's an instrument that can polarize the light, and if you put that into the path of the light, we'll see that all the planes will be stopped and only one plane of the light will be allowed to go. This is called as polarized light. This is a polarized light, but it is vibrating only in one plane. That's why we call it as plane polarized light. Okay, only single plane that is polarized of a light. So this is a plane polarized light. Now let's take a specific constant, let's say take a 0.1 mole concentration of R, okay, exactly 0.1 concentration of R in a solvent or something, or since it is a liquid, I guess it's an alcohol, we can just dilute it with water or something like that, and then you put it in a instrument, okay, and you put it into the path of the light. Now let's see what happens, right? So we said that this molecule actually interacts with the light, yeah, so it's the R molecule, and this, see, the plane of the light is vibrating in this direction, and when you put it into the path of the light rotates. In this case it is rotating counterclockwise, okay, counterclockwise rotation, and it is shown by this negative sign. Negative sign means the light has been rotated in counterclockwise direction. All right, what about S? If you take S enantiomer, make exactly 0.1 mole concentration of S, all right, and you put it into this in the same position in the same path of the plane polarized light. Let's see what happens. It rotates the plane polarized light in clockwise direction, okay, in clockwise direction by exactly the same degree, right, 13.5. So both of these compounds rotate the plane polarized light by the same degree but in exactly opposite direction. It is shown here by plus. Plus means that the plane polarized light has been rotated in clockwise direction, okay. So essentially the difference between these two compounds is the rotation, is the direction of the rotation of plane polarized light. There is no other difference actually, really. The chemical properties are same, the physical properties are same, but how they interact with the light, that's what set them apart. Now the question is, what happens, right? Now the reason for that interaction is the electron density, right? So you have a specific type of electron density around these molecules, and when the light comes, that light actually interacts with that electron density and it is rotated either clockwise or counterclockwise direction, okay. And there is no real way of actually predicting if the light is going to be rotated in clockwise or counterclockwise direction. There is no way of knowing this. The only way that we can know for sure if the compound is clockwise rotatory or counterclockwise rotatory is by actually doing the experiment. We have to put the sample into the polarizer and observe for yourself, all right, but you can't predict. So this compound that rotates the plane polarized light in counterclockwise direction is called as levorotatory, okay, and this compound that rotates the plane polarized light in clockwise direction is called as dextrorotatory, okay. Dextro means right, levo means left.